Okay, let's start. And today it's our great pleasure to have Dr. Yahui Chai from DESY. Yahui got her PhD from Peking University in 2021. And then she moved to Germany. DESY joined as a postdoc in the Center for Quantum Technology and Applications. And today, she's going to tell us about her work on simulating fermionic scattering on a quantum computer. Yahui, it's all yours.
Yeah. Okay. So thanks for Xiaojun. Yeah. I'm Yahui and I'm a postdoctor in DESY. So here today, my presentation is about how to simulate fermion scattering on a quantum computing. And if you have any question, you can interrupt me directly. So here first, it's a motivation. Firstly, the scattering process is very important to let us understand how the fundamental particles interact and also check our theory. But how to simulate this process in a classical way is still very difficult. Firstly, if we consider the traditional Monte Carlo method, it's not feasible for the real-time dynamics because of the sign problem. And secondly, if we consider the tensor network, there is a problem about the increasing entanglement with the time evolution. This means the tensor network will need more bond dimension, more computation resource, and this limit the tensor network to be only efficient for the short time dynamics. And but the quantum computing is promising for efficiently simulate the real-time dynamics, if we believe. So if we want to simulate the scattering process in the quantum computing, there are a few steps, and actually it's the same as your recently paper for the Hundred dynamics. Firstly, we need to prepare the vacuum, which is the ground state of the Hamiltonian. And secondly, we need to create the wave packets of particles on the vacuum. And then we do the time evolution on the initial state to let the particles move. Finally, we measure the observables in the final state. So here is the outline of this presentation. Firstly, it's the theoretical setup, including the introduction of the theory model and also about how to prepare the wave packet using quantum computing. And secondly is the simulation results, including the classical simulation for both non-interacting and interacting case, and also the real hardware ROM quantum simulation for the non-interacting case. So here is a theory model. In this work, we use a theory model to test our proposal. And this model is an exactly solvable model in 1+1 dimension. And here we use the staggered fermion to do the discretization. So firstly, this is a connected term for the fermion, and then the mass term for the fermion. And here is a full fermion interaction term. And in this work, we use a periodical boundary condition. So if we think about the scattering process, first we prepare the vacuum, the ground state of Hamiltonian, and this we can do by VQE. And secondly, we need to prepare the wave packets on the vacuum, and then we need to do the time evolution. this time evolution can be done by the totalization. So the first and third step are very clearly. So in this work, we merely focus on the second step, how to prepare wave packets for the fermion. I need to change it. Okay. And so firstly, we define the creation operators for fermion and antifermion wave packets. This is the fermion wave packets and antifermion wave packets. Phi k are the coefficients defined in momentum space and following a Gaussian distribution. And the operator ck dagger is a creation operator for a fermion with a momentum k, and the operator dk dagger is a creation operator for antifermion with a momentum k. And the relation between the creation operators defined in momentum space with the fermion operators in position space is here. We can use a Fourier transformation and a Bogoliubov transformation to relate them. And we can see for the fermion operator, fermion creation operator, it will create a fermion in position space. And for the antifermion creation operator, it will annihilate a fermion in position space. So that's why we call it fermion and antifermion. And then let's see the coefficients. We define a Gaussian distribution, and in the momentum space, so here the Gaussian distribution, the mu n related to the position of the wave packet in position space. And here the mean value mu k related to the momentum, and the sigma k related to the width of the wave packet. So here is a simple example. We define a Gaussian distribution in momentum space, and in momentum space here, the information of the location in position space is in the phase of the coefficients. And if we do the Fourier transformation to the position space, we can still get a Gaussian distribution. So here, the information of momentum uk will be the phase factor of the coefficient phi n. So now we have a definition in momentum space, and we can do the Fourier transformation to get the definition of the operators in position space. And we can see the coefficients in position space can also be got, and this related to the definition in momentum space and some constant related to momentum or mass. There is one factor, so Vk, we can see in the fermion, it will depress the coefficients on all the sides. So here pi is a projection operator for all the sides. And for antifermion, this factor will depress the coefficient for even sides. So here. And we can see this effect by this example. We define a wave packet in the momentum space for antifermion and for fermion. Then we do the Fourier transformation to position space. And we can see for the fermion, so it has a higher probability on the even sides. But for all the sides, the probability is much smaller because of the factor Vk. And for the antifermion, it's merely located on the other sides. And if we increase the mass, then this factor will be decreasing. And we can see the fermion almost only locate on the even side, and the antifermion almost only locate on odd side. So here is a short summary for the definition of operators. And so here we can prepare a vacuum by VQE, and we define the creation operators for we packet in position space. And here is some coefficients. This is decided by the momentum and the location in position space mu n and the width of the wave packet. And in position space, the effect of momentum will be the phase factor of the coefficients. And after we got this definition, then there is a problem how to realize this linear combination in quantum computing. Because in quantum computing, the multiplication is very easy. We just do U multiply V one by one. But for the summation of the operator, it's not so straightforward. And is there any question about the definition of operators here?
I have a short question. So on your slide, you showed when the mass is equal to 1, there is some non-zero content even or outside, depending on when we're looking at fermion, anti-fermion. Is a nature of this wave packet when mass is small, or is some artifact that we want to get rid of?
So it's merely because we use a staggered fermion.
Yes, but do you expect the wave packet should be completely on the odd side, or should completely be on the even side?
So only in the infinite mass limit, the fermion will only in the even side, and the antifermion will only in the odd side. And we show in the 100 mass value. It's basically this fact, right? And if we have finite mass, then we have this distribution. It's what we expect because we use staggered fermion. And if we relate this wave packet to the continuum limit, then actually we should do the average or do the summation of the even and odd side to represent one Dirac fermion in the continuum limit. Then we'll not have this strange oscillation.
Okay, thank you.
Okay, so yeah, then we go to the circuit for this operator. And okay, and still need to pay for it. So here we can relate our linear combination operator to a unitary transformation. So if we put the coefficients phi n to the first column of a unitary matrix, and then the creation operator for the wave packet will be the first operator after this unitary transformation. And why we need this thick unitary matrix U? Because for unitary transformation, we can find an operator V to realize this linear combination, so that we transform our problem of the summation of the operators to this multiplication of operators. This is more straightforward in quantum computing. And but there is the next problem is how to realize VU in using the quantum circuit. Because VU is very non-local, so it's a huge unitary operators. We do not want a very deep circuit depth. And so here the operator VU have a special property. It's homomorphism on the matrix multiplication. And so if we can find a decomposition of U, we can decompose this U to some local matrix. Then we can also find a decomposition of V to some local unitary operators. And luckily, we can decompose U using a given rotation to some local matrix. And here is the result of the decomposition of operator V using these two properties. This is a decomposition of U, and then we can get a relative decomposition of the operator V. And here the operator Vp and Vr are some local operators. After Jordan-Wigner transformation, we can see it's only some single qubit rotation gates and 2 qubit gates. In the following, I will use V5, V5C or V5D to represent this operator for simplicity. So here is a short summary for the V-packet preparation. First, we can define a creation operator for fermion V-packet and also the creation operator for anti-fermion V-packet in position space. And we can find a unitary operator V to realize this linear combination. And then we can decompose this unitary operator V using given rotation to decompose it to some local operators. So here is an example of the circuit for the V-packet preparation. So here we suppose the operator U0 be the circuit for the vacuum preparation. And in this box, it's a circuit for the fermion V-packet. And so firstly, there are some single qubit rotation gate which were related to the phase of the coefficient of phi, so related to the momentum. And then there are some 2 qubit gate and related to the magnitude of the coefficient. But there is a ununitary operator sigma minus because the Psi dagger and after Jordan-Wigner transformation, it's sigma minus, and it's non-unitary. So this circuit cannot be run in a quantum computing directly. So here we consider the whole process of the scattering. We consider also the time evolution on the initial state. So firstly, the vacuum preparation, we packet for fermion and anti-fermion preparation, and then time evolution. And then finally, we do the measurement. And as we mentioned just now, because sigma plus, sigma minus is non-unitary, so the circuit cannot be directly implanted. But usually we only care about some expectation values of the observables. So if we write the expectation of the observables, then it's this formula. So here, V phi still the circuit for the V-packet preparation, and the operator P, P4, P3 are the Pauli operators because of the sigma plus and the sigma minus. And in the kite, it's a similar formula, but maybe the P1 is different to P4, so we need a Hadamard test to measure this observable. So here, the observables we measured in this work is firstly is a fermion density, and we calculate the difference of fermion density with vacuum. And secondly, it's entropy. And so firstly is entropy as delta S1. It's a difference of entropy with a vacuum. And also to observe the entropy by interaction, we also subtract the entropy S1 by the entropy of individual fermion wave packet and individual anti-fermion wave packet to see if there are more entropy delta S2 generated because of the interacting. So here is our simulation result for the non-interacting case. So actually, we cannot call it scattering. It's just a free fermion propagation. And we prepare one fermion and one anti-fermion, and they with some momentum, and they move with the time, and they just pass through each other because there are no interaction. And because we consider the periodic boundary condition, so they go back from the other side. Besides, we consider more many few mass values. For heavier mass, the fermion have a slower propagation, and yeah. So let this show, and this is what we expect. And then for the free fermion case, we also observe the entropy. So firstly is a difference of entropy with the vacuum state. We can see more entropy generated, but maybe only because of the wave packet. And so then we subtract this entropy by the entropy of individual fermion and individual anti-fermion. Result in this plot, almost nothing left. Then we move to a more interesting case, the interacting case. If we consider a small coupling magnitude, it's almost the same as free fermion. They pass through each other. But if we increase the interacting magnitude, they meet each other and then and then go back. So we observe elastic scattering between the fermion and anti-fermion in this model. Besides, for the interacting case, we also observe the entropy. So first, the difference entropy with the vacuum, we can see they are the same, more entropy generated, and then we subtract it by the individual wave packets. There are still many entropy left. So this is very different with the non-interacting case, and this is the effect of interaction. Interaction generate more entropy in this case. And in final, we do the quantum simulation, do the real hardware run for the non-interacting case. And we use the IBM device and use some error mitigation technique. So here the system size is only 12 qubits. And we so the left plot is the ideal result from classical simulation, and the right plot is, so this time slides, we pick 5 time slides to run it in the hardware to do the comparison with the ideal result. So here's an example for the t equal to 0. and the hardware run result has a good consistent with the ideal simulation. T equal to 12 and T equal to 18. It's here. So yeah, that's what we did in this project. And so basically we propose a framework to simulate the fermion scattering on digital quantum computing. And we use a theory model to test our proposal. And also we run it in a hardware device, but only for the non-intempting case. And in the future, the most straightforward next step is to study the intempting theory model on quantum hardware. And also, this proposal is also feasible for other fermion models. And finally, but the most interesting thing is to extend this approach to the gauge models. Yeah, thank you. And here's all of our collaborators. And Vincent did almost all of the hardware run work. Thank you very much.
Thank you very much. It's a very clear talk, and the results are very interesting. Now we can ask some questions. Yeah, let me start one. So, in part of your talk, you showed us you decompose the V into a product of many V's, and that decomposition kind of relying on the theory has local interaction.
No. So we can see here the maybe here the definition of the creation operator of wave packet is not rely on the theory, right? It's just a linear combination of fermion operators. So for any theory, we can define an operator like this, and for this linear combination, we can use the same approach to define a V and decompose the V.
I see. I see.
Yeah.
Yeah.
Yeah. So the model you were studying, the Turing model, so I've seen this before, but I'm not intimately familiar with it. Can you just kind of give a background about why this is an interesting model to study?
So the most honest answer is it's easy because because we consider a fermion scattering process, and this is almost the most the simplest model, a fermion model. Yeah. And then why it's interesting? Because so first it has some similar property with the QCD, the how to say that? Asemic free property. Yeah. And also it can be exactly solvable in the continuous case, and it's a good model to test because we can have a result to do the comparison with theoretical result to see if our approach is promising.
Does it does it also has confinement?
No. So there can be single fermion in this theory, and that's why we can study the fermion scattering.
Okay, thank you. It's a very nice talk.
Yeah, just a follow-up question. Like, since you mentioned this model can be exactly solved, so we can compare, say, the quantum simulation or the classical simulation results with the known kind of analytic results. But how much computational resource do you need to be able to see that, to see the agreement?
Yeah, it's a good question and it needs many effort. So first, if we want to do the comparison, we need to go to the infinite value limit and the continuous limit, right? So yeah, it's a very many further work to do. But now we have some conclusions can be compared here. So in the theory model, there are many conservation laws, and this conservation laws give many limitations on the scattering process. So first, in this theory, the fermion number and the anti-fermion number are conserved separately. So there are no new particle generated. And secondly, the site of outgoing momentum should be the same as the site of incoming momentum. So the particles can only exchange momentum. This limitation will give us the conclusion there are only elastic scattering happen in this model. And we also observe an elastic scattering in our simulation result.
Okay, thank you.
I have a question on this slide, actually. How come when G is large, either positive or negative, the particles bounce off of each other? Why don't they ever pass through each other? Like I would think if there's attractive interaction, maybe they would go through each other. It looks like they always bounce off of each other.
Sorry, I didn't hear your question clearly.
So like in this first plot here, you have G is minus 0.8.
Yeah.
And the fermion and the anti-fermion bounce off of each other.
Mm-hmm.
And the same thing when G is positive 0.8. I'm surprised they don't pass through each other. Do you know why that is?
You mean why if we change the sign of G, they do not pass through each other?
Yeah.
If interacting strength is weak, then they pass through each other. But if we have a strong enough interacting, it's why they should pass through each other.
I mean, naively, I think if they're attractive, they get pulled towards each other and could move through each other. But it seems like that.
So yeah, in this model, for the positive G, yeah, it's true. There is an attractive force between fermion and anti-fermion. Yes, that's true. But because we just said there are only elastic scattering can be happening in this model. So we cannot observe a very close path between them because that means the momentum changed.
Okay, thank you.
Oh, yeah.
Did you look at like in these G not equal to 0 plots, did you look at like particle production at all? And like kind of what is produced when the wave, aside from just entropy, like what's produced when the wave packets collide?
Can you repeat your question?
I guess, were you only looking, so when you collided these wave packets, were you only looking at the entropy production? Or did you, what else might be produced?
You mean to observe more quantity?
Yeah.
No, so now we only observe the fermion density and the entropy. And if you have more interesting suggestion, welcome.
Okay.
They have the chart, sorry, they have the particle number constellation. Oh, yeah.
But maybe if I could follow up on this, I mean, the model is integrable, right? It's beta ansatz and it's two particle reducible. I mean, you cannot get anything else than elastic scattering, right? I mean, will not. Is that true? I mean,
you mean no bound state generated, right?
Yeah. I mean,
Yeah. So yeah, only elastic scattering. So
then Then maybe if I could, so you can actually make, there's a model called the massive Schwinger theory model, which is kind of the Schwinger model, but with this interaction term, and that's not integrable. Have you looked at that model?
You mean the Schwinger model?
Yeah, but the Schwinger model with the Thirring term, there's a paper by Coleman, I think from 75. So it's actually quite a cool model. So it's the combination of the two models, and it's not integrable. Have you looked at this?
So is this model has a confinement of the fermion?
I think it depends on how you tune the couplings, but I think there's I think it's essentially the phases are, well, I could be wrong here, but I think the phases are very similar to the Schwinger model itself, and that is confining except at theta equals pi. So I think it's yeah. I don't know, maybe if you make the Thirring term very large, then it looks more like the Thirring model, but yeah.
Okay, yeah, that's interesting. So because we so now the current setup is only about the fermion scattering, so we can't do the same thing in a model has confinement. Yeah. So you mean the Schwinger model with this in additional interaction term?
Yeah, right. But if yeah, exactly. And if you have the Schwinger model, right, you can have a theta term and so on, and unless you set it to pi, it's confining. Because electric fields cost you energy, and then if you're in the confining phase, you can actually have mesons, and you can scatter mesons and stuff like this. So it's actually an even more interesting model.
Yeah. Okay. Yeah, that sounds also interesting. I will have a look at this hybrid model.
Okay. Yeah.
I have one more question. So the wave packet you prepared is in the non-interacting theory, right?
Yeah.
But when you go to the interacting theory, presumably this should change. Like the wave packet should be different. Is that true?
So basically, the most I think the most important part here is to define the momentum operator, right? We have superposition of some momentum operators, and we have a wave packet, and the momentum operator is not changed for the intending and non-intending case in this theory. So we can still use the same definition for the intending case. And yeah.
Okay, thank you.
Yeah. Any more questions? Just go ahead. So, any final questions? Also, online participants, if you want to ask a question, just unmute and ask.
Yes.
I heard something like no. Okay, if no more questions, let's thank Yahui again.
Thank you for the invitation.